Welcome to this video in the periodic table chapter. This is 4.3, periodic trends. In this two-part video, we are going to discuss periodic versus group trends, talk about how the placement of an element on that periodic table will relate to that atom or element structure and properties, dive into coulombic attraction, atomic radius, ionization energy, and electronegativity. If you haven't already done so, please make sure you have a chemistry notebook, writing utensil, periodic table, and your C-cert at the ready, because we are going to need it. So without any further ado, let's get cooking. Trends on the periodic table. What exactly are they? Well, periodic and group trends are patterns and properties that repeat in regular intervals on the periodic table. And so we just said that there are periodic and group trends. Periodic trends are trends that will be predictable and repeat across a period, which you guys can see here. We have period 4 illuminated. And group trends obviously are trends that are predictable and go up and down within a group. This video is going to break down a bunch of periodic and group trends. And no matter how any of those change, understanding why the property changes and being able to predict how it changes is all based on your knowledge of atomic structure and coulombic attraction, which, if you remember, we did a POGL on, and the POGL delved into how distance from the nucleus of an electron will affect the attractive forces between that nucleus and the electron, and how the increase in the number of protons, which increases the nuclear charge, will affect the level or the degree of attraction between a nucleus and electrons. All of those things influence our periodic trends. And there are many periodic trends. In part 1 of this video, we're going to be covering atomic radius, ionization energy, and electronegativity. Part 2, we're going to cover the rest that are here, but there are a bunch that are listed on table S of your C-cert along with their values. So if in a pinch you don't remember how the property trends, whether the numbers go up or they go down, you could always really look at table S and use that data to extrapolate what the changes actually are. And I'll show you how to do that in this video. So without any further ado, let's get into the trends and start talking about atomic radius. The first thing you have to know about atomic radius is it generally tells us the size of an atom, and that size unit is the picometer. If you've never heard of a picometer before, basically if you had 1 meter, you would wind up having 1.0 times 10 to the 12 picometers, which means it's an incredibly small unit of measure. So radius, on the other hand, is something that you should know. If you remember from math, radius is essentially taking half the distance across a circle from the center to the edge here. And for an atom, it is pretty much the same thing, except there's an issue. The problem that we have is that when you're dealing with atoms, atoms do not exactly have a discretely defined edge that we see here on a circle. Of course, this here we have is the Dalton atom. All of the atoms we're dealing with nowadays have the electron cloud dealing with probability regions. So it's almost like we have a feathered edge out here. To determine radius, you can't really say, well, I'm going to go from the center to the end of the feathered edge, because you really don't know where the end of the edge actually is. So to get through that and get by the fact that it is a cloud, what scientists decided was they would take 2 atoms and put them adjacently next to one another and then measure the radius. They decided that since the nucleus is the only well-defined portion of an atom, if we put the 2 atoms next to one another and took half that distance between the nuclei, assuming the nuclei was the center of the atom, we would essentially get the radius of the atom. So our first definition is atomic radius is half the distance between 2 adjacent nuclei. Make sure you copy that down in your notes and start to memorize, because as we said before, you cannot speak the language of chemistry if you do not know what the words mean. So knock that down now. All right, let's play. How about we take group 1 and we try and predict what the trend is. Using our knowledge of atomic structure, as we go down the group, will the radius be increasing or decreasing? Stop the video now and then make your prediction. Okay, now what we got to do is we got to figure out what the trend is. So let's dive into table S and see what the atomic radius of lithium will be. So lithium on table S is 99 picometers. And let's go down and check something at the bottom of the group so we can see how it trends. Taking cesium is 238 picometers. So indeed, what happens is as we go down a group, radius is going to increase. Now, let's talk about why. Understanding why radius will proceed as we go down group 1 is pretty simple, and it all comes back to the fact that structure of an atom determines its properties. And in this case, we're talking about the property of atomic radius. What we need to consider is what's going on with this atom. And if we look at lithium, lithium has 2 principal energy levels because it's in period 2, and something like rubidium, because it's in period 5, has 5 principal energy levels. As we proceed down the group, the addition of each principal energy level winds up increasing the distance from the nucleus, which in turn increases the radius. Remember, we said we had 99 picometers, and here we had 238. Those electrons that are way out here don't have the attraction that the electrons that are closer have, and as a result, they kind of float further out and don't get pulled in. To help you guys make sense out of periodic trends like atomic radius, I'm going to introduce you to something called the Ogre postulate. And the Ogre postulate is one of our creations here in room 304, and it basically says atoms are like ogres, which are like onions, if you remember this scene here at the farm from Shrek. Shrek goes on to tell Donkey that ogres are like onions, and Donkey makes some snarky remark about Shrek's breath, and Shrek says, "No! Layers!" And the fact that they have layers really is sort of what we're getting at here. You'll notice that this onion here looks a heck of a lot like a Bohr atom, and every time we add a successive layer to the onion, the radius or the size of the onion grows. And if you keep on adding energy levels, you'll notice that with every successive layer, the electrons that are here are further away from the nucleus. And so we see that here in this picture that I pulled from our POGL, where the electrons that are only 2 energy levels away from the nucleus with lithium have a greater force of attraction than the ones that are 4 energy levels away in potassium. So that is the Ogre postulate. Tuck that in your pocket, it's going to reappear. Now that we got the group trend in our pocket, let's now see how atomic radius trends across a period. I want to direct your attention to period number 3, where we are going from sodium all the way over to argon. So stop the video now and make a prediction. Do you think atomic radius will increase or decrease as I proceed left to right across the periodic table? Pause the video now and then unpause when you have an answer. In order to make heads or tails of this trend, the first thing we're going to have to do is look at the structure of the atom. And the first thing you're going to notice is that since we are in period 3, all of these atoms will have 3 occupied principal energy levels with their valence electrons in the 3rd level. So all the electrons are approximately the same distance from the nucleus. So that's not exactly something we can look to answer the question as to why argon would technically be smaller than sodium is. The real answer lies in taking a deeper look at what is going on in the nucleus of these atoms. If we look at the nuclear charge of each one of these, and you can see here it starts at 11 and successively moves up by 1 up to 18, we've added 1 extra proton as we proceed left to right from atom to atom. That extra proton is important because as you can see here, when we go back and look at what happened in the POGL, the addition of an extra proton does increase the force of attraction on an electron, especially when all the electrons here are approximately the same distance from the nucleus, which all these electrons that are here are. So if you think about it, it is the fact that the effective nuclear charge is increasing and the outermost electrons are now more attracted to the nucleus and therefore pulled closer to it. So in argon, where we had 18 electrons, those electrons were more attracted to the nucleus than they were in sodium, where we only had 11. And as a result, the argon atom was smaller. All right, so that is one trend in the books. Let's move on and start to talk about ionization energy and electronegativity. Let's do ionization energy first. The rationale of ionization energy lies in the fact that when you remove an electron from a neutral atom, you create an ion. And this we know, taking one electron away makes a +1 ion. But as you can see here in this equation, it requires energy to remove that electron. And let's think about why for a second. If we are looking at this valence electron here, you have to understand that this electron is attracted to this nucleus that's here. And in theory, it doesn't want to be removed because it is being pulled towards the nucleus. So you have to overcome that force of attraction. So by definition, ionization energy is essentially a measurement of the amount of energy which is going to be required to remove the most loosely bound electron from the valence shell of an atom. And so as you guys will see, because the nuclear charge differs in all the different atoms that are there, each atom is going to have a different amount of ionization energy. So it's up to you to know what the trend in ionization energy is going to be. Okay, let's now repeat the activity that we just did. Let's make a hypothesis. Based on our knowledge of atomic structure and periodic trends, will the ionization energy increase or decrease across a period? And will it increase or decrease down a group? So pause the video now, make your hypothesis, and then unpause when you're ready for the answer. All right, so the only way to truly know how this is going to trend is to take a look at your CSERT, Table S. So if we dive into the CSERT and we go look for our values, ionization energy is the first numbers we come to as we are going left to right after the name. It looks like to me that across a period, we are going to have 496 kilojoules per mole for sodium and 1521 kilojoules per mole for argon, which means across a period, ionization energy is going to increase. All right, time to look down a group. It looks like to me we start with 496 kilojoules for sodium, which is here, and at the bottom of the group, there's 376 kilojoules, so down a group, ionization energy is going to decrease. So now it is time to talk about how structure is going to dictate this property. So thinking about the atom and considering what we just talked about with atomic radius, you guys should now understand that as you go across a period with each successive element, we continually add one proton, and as a result, the nuclear charge is increasing. So the coulombic attraction between the nucleus and the valence electrons starts to get stronger. And when the attraction between the nucleus and valence electrons is stronger, you have what we call a more effective nuclear charge, which simply means that increased attraction makes you need more energy to forcibly remove an electron from the valence shell. So considering lithium here, we know it has a +3 as its nuclear charge, and we know neon has a +10 as its nuclear charge. Look at the difference here. Right? It's almost 4 times the amount of ionization energy to remove an electron and create an ion for neon than it was for lithium. It's much easier to remove electrons from your metals that are here because relative to the non-metals, they have a far weaker nuclear charge and a decreased attraction on the valence electrons. If you're saying to yourself, man, that certainly sounds familiar, we can throw it back to the time that we saw the same relationship happening in Model 3 of our Poggle. Here we have one proton, which is attracting one electron with a force of 2.30 times 10 to the -8 newtons. And when you successively add a proton, you'll notice that the attraction starts to increase. And when we get down to Model F, which is here where we have 4 protons, the attraction on that one electron winds up being 9.2 times 10 to the -8 newtons. So the attraction starts to increase with the increase of the nuclear charge. Okay, let's now talk about the group trend of ionization energy. You guys remember when you looked it up in the CSERT, we got 496 to 376, and as you went down a group, the ionization energy decreased. Let's talk about how structure will dictate and determine your properties. As you guys remember, every time you make your way down a group, When you're jumping from period to period like this, you know you have the addition of a principal energy level. And if you remember back when we were talking about the atomic radius, the addition of a principal energy level increases the size of the atom. And if you increase the size of the atom and you push those valence electrons further away from the nucleus, you technically will be decreasing the attraction, or you will be reducing it. So it will actually take less energy to remove the valence electrons. So distance will decrease attraction. That is an important concept. It is so important that we have given it its own wacky analogy. Introducing to you guys the girlfriend postulate. Here you see high school sweethearts. They've been dating for 2 years. They are very much in love. But at the end of the summer, the boy is going off to college, and when he gets to Harvard, well, he's so far away from his girlfriend at home that he makes new friends with this girl over here, because the distance that he is away from his former girlfriend, who's right here, has decreased his level of attraction. And that's exactly what we're seeing here in this model that we saw in the POGL, where if you take lithium, for instance, lithium's valence electron is in the second principal energy level, and it is relatively close to the nucleus, so there is a strong coulombic attraction between the positive nucleus and the negative electrons that are here. When you go to sodium, sodium's valence electron is another principal energy level out. So the level of attraction is less than lithium's was. And then finally, when you have potassium, where the valence electrons are in the fourth principal energy level, they have the least attraction to the nucleus. So if you guys can remember that in the girlfriend postulate, distance decreases attraction, you will understand why the ionization energy decreases as you proceed down a group. I wanted to take a second to talk about what is called second and third ionization energy. So if you are taking Regents chemistry, this is not something that's on the Regents exam, but if you are in honors or are taking AP Chem, this is an important topic. If we look at this graphic that we see here, where we are talking about all the ionization energies, you'll notice that this graphic goes so far as to go from first, second to third to fourth to fifth ionization energy all the way up to seventh. And you will notice that there is a staircase that is here. You'll notice that there is a very large jump between the ionization energy that is in beige and the ionization energy that is in blue here. What is it that accounts for this large jump? So for instance, in sodium, it's after the first electron is removed. In magnesium, it's after the second. In aluminum, it's after the third, silicon the fourth, and then phosphorus the fifth, etc. In order to understand why we have such a large jump, you have to think of atomic structure. Let's take sodium here as an example. Once we remove that first electron and we put 496 kilojoules worth of energy to remove that 1 mole of electrons, you'll notice that you have exhausted all the electrons that are in this principal energy level. And now the next electron you were going to remove winds up being in the second principal energy level, which is much closer to the nucleus. As we learned in the last slide with the girlfriend postulate, distance decreases attraction. So as we are moving closer to the nucleus, right, the closer you are, the greater the coulombic attraction is. So for us playing along at home, the largest jumps in ionization energy are always seen when that final electron is removed from the higher energy level and the subsequent electron is removed is part of a lower one. So it has to do with the fact that the distance in that lower energy level is much closer to the nucleus, which increases attraction, which requires more energy to pry that electron loose. So that is second and third and fourth and fifth ionization energy dependent on the atom that you have. The last trend I want to dive into is called electronegativity, and electronegativity will help explain why there are just some atoms on that periodic table that have a much easier time gaining electrons than others. By definition, electronegativity is defined as the relative ability for an atom to attract electrons to itself when it chemically combines with another atom, which means when it is going to initiate chemical bonding. You can shorten that definition and just say electronegativity is the relative ability for an atom to attract electrons. Electronegativity works on a 0 to 4.0 scale, with fluorine being the most electronegative element, clocking in at 4.0. Cesium and francium are the least electronegative elements, and you would think they might have a value of 0.0, but they actually don't. They are less than 1, but they are somewhere living in the 0.7, 0.8 range. Basically, the way it works is the higher the electronegativity value, the greater the tendency for an atom to attract electrons. All right, let's play the game for the last time. What would you expect the trend in electronegativity to be, given what you know about attraction between protons and electrons in an atom? Will electronegativity increase or decrease as we go across a period and as we proceed down a group? So make your predictions and then look up the values on your CSERT and see if you were right. Okay. So it looks like to us that if lithium clocks in at a 0.9 and fluorine is a 4.0, when I go across any period, my electronegativity is going to increase. And it also looks like if I go down a group, and we chose the halogens here, fluorine is a 4.0, all the way to iodine is a 2.7. Looks like electronegativity going down a group is indeed going to decrease. We can confirm that by looking at this nice graphic that we see here, where the top members of each group have the highest electronegativities, and as you're proceeding left to right on the periodic table, our electronegativity values are indeed increasing. In order to explain the periodic trend of electronegativity, you have to think about what is happening as we go across a period that might make atoms at this end of the periodic table more likely to attract electrons. And you know what? You guessed it. You have to think, what is it that attracts electrons? Well, it's protons. And as we saw before in this video, as you proceed left to right in the periodic table, every successive element adds one more proton, which increases the nuclear charge that those electrons are going to feel. So in a period, each one of these elements also has the same degree of shielding, with the valence electrons in the same principal energy level. So what winds up happening is, with more protons in the nucleus, we have a greater attraction for electrons. The ability to attract electrons goes up, and as a result, we get a higher electronegativity. Turning the page over to the group trend, why does electronegativity decrease down a group? Well, it's simply because structure does indeed determine properties. Let's go with this. As we proceed down a group, you guys know it's the Ogre postulate. Every successive element down a group has one more electron energy level than the previous atom before it. By adding those extra energy levels, we are theoretically increasing the size of the atom and making the electron cloud larger. That is technically going to decrease the attraction on the electrons and lower your electronegativity value. You're also going to have your nuclear charge shielded by all the inner electrons that are in there, which is technically decreasing its ability to see through there and attract electrons into the valence shell. In addition to the Ogre postulate, we have the girlfriend postulate at play here to help explain why the electronegativity values go down for the larger atoms. Remember, the girlfriend postulate says that increased distance decreases attraction. So the larger atoms, as we said before, have valence electrons and valence shells that are further away from the nucleus. If they're further away from the nucleus, they do not feel the attraction of that nuclear charge and are less likely to attract electrons and put them in that valence shell. So when we talk about the relative ability to attract electrons, the much larger atoms in the group always have the lowest values. So that is it for me. Make sure if you guys have any burning questions, you bring them to the burning questions segment in our next meeting. It's been a pleasure taking you through part 1 of periodic trends. I'm looking forward to part 2, and I will see everybody on the flip side. Peace out.
That's all, folks.